Hello everyone, I'm Jialin from Timecho. I'll share with you about the Intelligent Industrial Data Foundation of Apache IoTDB 2.0 in the AI era. I'll give you a detailed introduction. In the AI era, IoTDB provides new features, versions, and capabilities. These mainly include three parts: data infrastructure, intelligent infrastructure, and a full chain ecosystem. All right, some of you may have heard whether IoTDB 2.0 has a data mode or a table mode, or perhaps you've come across the concept of dual modes. So where did this concept actually come from? Let's first look back at the more than 10 years since our inception in 2011. We've always focused our work on two aspects of data. The first aspect is data management, which is about managing the data itself. In terms of data management, we've gone from the earliest industrial relational databases to distributed architectures, then to the collaboration between end device, edge, and cloud, and by 2024, we've reached peak performance, topping international rankings. All of these efforts have revolved around managing data. So in the AI era, what new features or challenges has data management brought up? Actually, if we look at industrial monitoring scenarios, the value of real-time data generally decreases as it gets older. In other words, the newer the data, the more valuable it is. But in the AI era, the data we need to analyze is no longer limited to just the most recent data. Instead, it's about which data holds greater value, data that reflects the status and characteristics of the equipment and can indicate its operating conditions. Such data could become high-value data at any time. That's also why people say this. In industry, some events may have very small sample sizes, and these small sample events are extremely valuable. In other words, when conducting industrial analysis, any data segment, any real-time data from any period can be pulled for analysis anytime. Moreover, its analysis is characterized by randomness and large-scale features. So compared to the AI era, where people used to focus more on large model algorithms, in fact, we should pay more attention to the greater challenges these large models and algorithms pose to data. This means that in the AI era, data infrastructure has also become even more indispensable. And it has become an even more important component. This is the using data part. Going further up, it's actually the AI part related to data usage. In this regard, after the database has collected all the data, the main purpose is actually to bring value to users, how to analyze data to extract its value. Here, we provide continuous syntax and some quality libraries to improve data quality, including AI and SQL over the past 2 or 3 years, as well as our current built-in time series, large models, and so on. In the new AI era, people have actually raised even more advanced challenges regarding how to mine the value within data. So, what exactly are the new features that IoTDB 2.0 offers in terms of data management and data utilization? Next, we'll give you a detailed introduction. All right, the first part is this: solid data infrastructure. Here, we actually encounter the first scenario, which is the dual mode concept we mentioned. Let's review how its design approach has evolved. First of all, our industry has gone through a stage of digitalization, where at the beginning, everyone focused on how to quickly capture data. Collecting and managing data became the main concern. So, in order to gather data more quickly and manage it in a unified way, we actually need to provide a hierarchical modeling method for devices in industrial scenarios. This modeling approach allows our on-site OT personnel can effortlessly map how the data they need to collect is organized in the physical world into the IoTDB, using a tree structure for management. This was our original intention, to enable data to enter the database in the most convenient way possible. So this is also the origin of the tree model. In the next part, we actually move on to the stage of using the data. After an enterprise has built such an industrial monitoring platform, the next step is how to conduct large-scale analysis and utilization of this data. At this point, you might encounter a lot of data warehouses and big data platforms, but in traditional solutions, these two aspects are usually separated. On one side, you have OT for actual monitoring, and on the other, you have IT for real-time operations. For offline analysis, there is usually a traditional ETL process in between, which comes at a high cost. We need to migrate and reorganize the data, and all of these are costly steps. So with IoTDB 2.0, we hope that people in the IT field, who all really like to use SQL for data analysis, can benefit. That's why we believe that in terms of analytics, the table mode is actually the user's first choice. So this brings up the question of how to bridge the gap from OT to IT, and how to enable a deep integration between these two domains. It's actually a process of deeply binding and connecting the tree mode with the table mode. All right, next let's take a look at its specific capabilities. First, when we ingest data into ITDB, we might organize and model it in a tree-like structure. Then, if we want to perform more analysis on this data, including using some standard SQL capabilities, For things like aggregation queries and so on, we can use a single SQL statement to create a table on this tree. This table is actually a virtual view, and this view doesn't take up any space. It's essentially a mapping from the tree mode to the table mode. In this way, we can analyze our data using SQL, which is a method that analysts are more familiar with. In this way, the operations staff see a tree structure and enter data into it, while the analysts see a table. This allows for more convenient and efficient analysis on top of it. This creates a unified data foundation for both OT and IT. This data doesn't need to be migrated or reorganized. All that's needed is a SQL statement, the function to create table views. In this way, OT and IT are integrated. So that's the first aspect. The second aspect is, if in our original scenario we use traditional relational databases like MySQL or tag models like InfluxDB, then how can we conveniently migrate that data over? At this point, we can also directly create a table, but this table is not the same as the view we mentioned earlier. It's an entity. The characteristic of an entity is that the table can not only be queried, but it also has a greater capability. It can be written to directly. In other words, if we want to reduce the cost of migration, we can actually create a table entity to handle both reading and writing. This way, what the user sees is just a single table. At this point, we leverage the capabilities of IoTDB's underlying storage engine. This allows flexible data storage based on our original time series model engine. Thus, we've implemented the dynamic wide table feature. This table has the same flexibility as the time series model. When collecting data, we might not know how many measurement points our devices have, and new points can be added anytime. In this case, we can let this table expand dynamically as data is written, with no upper limit to the number of columns. With traditional databases, we all know that a database table usually has an upper limit of a few thousand columns. But when managing high-end equipment like large airplanes, a single plane might have tens of thousands of columns. In that case, you no longer need to hassle with splitting databases in tables. These are the two aspects of tables, views and entities. All right, so next, on top of the SQL language, we've also added a lot of time series analysis features. The first one is trend queries. When we talk about real data and what people are actually analyzing, the first and most intuitive thing that comes to mind or catches our attention is its trend, whether it will go up or down tomorrow, whether there's a peak or a trough. These shapes or trends actually represent the operating state of the equipment. For example, maybe today the equipment feels unhappy, and suddenly there's an upward spike. These events are exactly what analysts need to pay attention to. Traditionally, we might import this data into our application systems and then write analysis algorithms to match data. We might even try to measure similarity between two sequences, like comparing two blood samples. But no matter which method we use, complexity is always high. Here, we've introduced a standard SQL capability, which is also a framework for trend queries. In fact, it's part of the standard SQL specification. It's called pattern matching or row pattern matching. What can it do? It allows you to define patterns to specify what an upward trend means, what a downward trend means, and then to piece these subpatterns together. In this way, you can describe a complete trend. So using something like up, down, and then up again, we can describe a trend that first rises, then falls, and then rises again. With this kind of description, we can quickly identify the sensitive trends in the time series that we care about. It helps us accomplish the first analysis of time series data. The second analytical capability is window functions. What's the biggest difference between time series data and other relational data? Time series data has window semantics. When we analyze real-world data, we don't just look at a single point, we look at a window. We want to know whether this window is trending up or down, what its slope is, and so on. This gives us deeper analytical capability for real-world data. So here, we've also provided the powerful capability of standard SQL window functions, which can perform things like cumulative statistics, detailed trend analysis, and anomaly detection, such as carefully examining the slope and so on. The second extension for data analysis in IoTDB, and the third part, is UDF, user-defined functions. It allows you to put business-specific data operations directly into the database, integrating data and computation. So, what have we done? We've provided a top-tier enhancement for this capability. Currently, most time series and UDFs supported by relational databases are of two types: scalar functions, which are one-to-one transformations, and aggregate functions, which are many-to-one transformations. But both impose quite a lot of constraints on data analysis paradigms. However, if we want to perform more flexible data analysis, for example, if we map a time series to its frequency domain, it might contain multiple components, so its output is no longer a simple one-to-one or many-to-one mapping. This is where the power of table-valued functions comes into play. They can take any table, process it with custom logic, and output another table. these two tables can look completely different. Their rows and columns can all be user-defined. So the ability to integrate data and computation has been upgraded from standard to top tier. All right, so this is one of the capabilities we provide in the UDF area. Next, let's look at queries. Let's start with an example, querying for voltages greater than the average. Previously, to do this analysis, you typically write two steps in your application. First, query for the average value, read that out, then construct another SQL query to fetch data where voltage is greater than that average. This increases the complexity of our business programming and adds to the complexity of network exchanges between the application system and the database. So how can we reduce this? Actually, it's by using subqueries. With subqueries, we can handle this kind of complex data processing with just a single SQL statement. With this kind of nested logic, we can greatly simplify the interaction between the application system and the database. All right, that's the fourth capability. So up to now, we've also demonstrated the table mode and the richer time series structure queries and analysis syntax that can be extended on top of the table mode. But actually, that's not all there is to version 2.0. IoTDB 2.0 is more than just SQL. Next, I'll further introduce what else we've expanded in this 2.0 version. Let's take a look at what new challenges the AI era has brought to data management. Just now, we mentioned some things related to analytical syntax and applicability, but actually, as Professor Wang also introduced earlier, data in the industry is not just time series data. There is a kind of description that time series data is the lifeblood of industry. It's like the electrocardiograms of machines. It may account for 60% to 70% of all industrial data, so it's absolutely the core. Many state analyses are also based on time series data, but time series data alone isn't enough. We also need context. We may need to look at things from a business perspective. For example, how do my machines operate when it rains today? Or what is the working condition of our equipment when the voltage is at a certain rated threshold? So almost all business analyses are interdisciplinary and require data association and integration. Therefore, the next major goal of IoTDB 2.0 is to move towards association and integration. The first question is whether we can support static attributes of devices. This is also the most frequently raised issue by users since IoTDB was launched. People might say, my devices don't just have real-time data. They also have some static attributes, like their model or certain components. These are often prerequisites we need to analyze or filter by. So in the IoTDB table mode, what we just saw actually only included the left and right parts. That is, how to locate the device's components and how to manage these dynamic, real-time data. But in the table mode, we've actually added another important part, which is the purple section in the middle. This represents some of the static attribute data of our devices. It doesn't change over time. It's fixed according to some factory settings of the device. So these things are actually what we use for an important capability for associating time series and static data in analysis. Now, we can say this table is a time series table, but it's not just that. In fact, it's a table that integrates both time series data and static data, a fusion of dynamic and static information. This is an even more powerful capability brought by 2.0 version. Besides the static attributes of device components, we can also apply various filters, and after filtering, we can query the relevant actual data. All right, so this is the enhanced analytical capability that this table provides. Now, aside from structured data, some users mentioned, in addition to static data and some related static information, they also have certain object files. For example, in some scenarios, there are also blueprints, documents, BUM information for certain components, and even images and videos. Can these unstructured data and objects be managed together with IoTDB? That way, I don't need to manage time series data in IoTDB and small files in the file system separately. Is it possible to accomplish the integration and association of these two models in business logic? The answer is yes, it is possible. In our database's data model, we've actually added an important type, which is the object type. Previously, people might have stored these various objects as binary or blobs in IoTDB. But with the object type, we can now store user-defined formats and also work with these formats. We can parse them using formats familiar to our business. For example, if we have an industry-specific file that we want to store in the database, at the same time, we also want to leverage the database's query capabilities. We can push down some internal file operations to accelerate file processing at a deeper level. This approach can now be implemented using IoTDB's current capabilities. As shown in this diagram of a test flight mission, in addition to time series data, we also have objects, documents, images, and videos, all managed and analyzed in a unified way within a single data space. This truly achieves a multimodal fusion. All right, there are also some external data sources. For example, we might store data in MySQL, Hive, or HBase. These data may not relate to the device attributes we've mentioned. They might be associated with production scheduling, factory settings, or information. So, can we support cross-database federated queries? Actually, we've worked on this as well. We've taken it a step further. Here, we've added a module to the integrated query engine on top of the table mode and schema. We've introduced a module called federated query. This module allows us to read data from external data sources or tables into this space. This way, we can associate and integrate these data with our time series and static data for analysis. We've also managed to extend and implement this using our table modeling capabilities. So now, if a system uses both IoTDB and MySQL, where we previously needed to do heavy joining or computation at the business layer, now we can accomplish multimodal data integration within IoTDB using just a single line of SQL statement. That concludes the part about IoTDB's new multimodal data management capabilities at the infrastructure layer. Next, let's talk about the second part, the innovative smart platform IoTDB is doing in the AI era. Let's start with what happened when large models emerged. Everyone hoped that these models could solve some of the domain-specific pain points that have troubled various industries and sectors. However, after long-term exploration, we've found that whether it's a large language model or any other general-purpose large model, none can solve these problems well. The main reason is that general models don't understand our domain knowledge, or you could say they don't know the mechanisms behind our equipment and processes. At the same time, when we use models for either training or inference, the quality of the data in our databases also affects the performance of our models. These two factors are the biggest obstacles preventing us from applying intelligence to our industrial operations. So how do we address the shortcoming? That's the core of our solution. There are mainly two aspects here. The first is high-quality domain data. After more than a decade of refinement, we've actually been able to manage our business data at a high level of quality through our data nodes, including unified modeling and improving data quality, as well as data processing. All of these are foundational tasks that have actually already been completed. So for IoTDB to directly solve users' domain-specific business problems, there's only one thing missing, model fine-tuning. So what does model fine-tuning do? It allows a general large model to be mapped or focused into a model that addresses domain-specific problems. Only with this model can we help industrial users solve real-world problems. Next, let's look at the IoTDB AI node and data intelligence architecture. To the right of the data node is our architecture, consisting of several components, with the most critical the model management layer. When we talk about model fine-tuning, what model are we tuning? When people hear about large models, they think of large language models, whose main application is a question and answer assistant. In the industrial field, we analyze the operational status of equipment and data. The foundation for our fine-tuning is our time series large model, Timer. Professor Long will share key technologies of Timer in more detail. Now, based on this large model, we do two things. The first is data preprocessing. So what does data preprocessing actually do? It's about further organizing and integrating the raw, low-quality, real-world data we've collected. This includes aligning the timestamps, regularizing the frequency, and filling in any missing values. Only after preprocessing the data can we turn the dataset into something usable for the model. Then, moving up another level, we've developed a large-scale engine called the training engine. This training engine allows us to fine-tune our foundational large models, as well as other models, with just one click. During the fine-tuning process, there may be multiple rounds of training, and throughout these rounds of fine-tuning, we also evaluate the models to make selections. We determine which round of fine-tuning yields the best results to obtain the optimal model from that particular round. This is how we achieve it. With just one SQL statement, we can fine-tune the model. If we look at this SQL, there are actually two important pieces of information. One is from model. The from model part specifies the model algorithm for fine-tuning. Below is a dataset. For this dataset, we can specify data in a database we want to use for fine-tuning. It could be incremental data from a device on a particular day. This way, the model is managed within the database. For example, after a week, I fine-tune the model with that week's data. After another week, I fine-tune it again with the new week's data. This allows the model to be incrementally updated online. Thus, the model can always keep up with the latest status of our devices. It ensures daily changes are not overlooked. With the one-click fine-tuning feature of the AI node, we can quickly build a large time series model tailored to your specific field. In this way, Actually, as a database developer, training and fine-tuning models used to be quite a heavy task for me. There was a lot of manual work. I had to write some Python code externally to extract data from the database, and then I often had to convert and process it in various ways for cleaning. Finally, I'd have to train a model and then use it for inference. The whole process was tedious and inconvenient. But with the one-click fine-tuning of the AI node, a phrase echoing in my mind, reaching for the stars with your own hands. In other words, time series large models are no longer out of reach. They've become something that's right at our fingertips. Anyone who has data can now have a time series large model tailored to their own field. This capability is designed to provide everyone with an extremely convenient tool. All right, let's take a look at the effectiveness and efficiency of fine-tuning. With incremental data at the second level for one day, using a single GPU for fine-tuning, it actually only takes about 5 minutes or even less to complete incremental learning. In other words, every day, it takes less than 5 minutes for us to obtain an updated model. With this model, the statistical metric, mean squared error, on the full dataset can be reduced by more than 20%, which is quite a good result. Now let's look at the intuitive performance. Before fine-tuning, the model's predictions may deviate significantly from the actual sequence, making it almost unusable in production. This is actually very easy to understand. Time series data differs from language data. It reflects device mechanism changes, not language's logical flow. In language, if I say one sentence, people can generally guess the next. But with time series data, it's different. Its next second changes are quite unpredictable. We can only learn from past patterns to predict. After fine-tuning, it better aligns with the real trends and changes in this data. All right, let's look at the overview of the Industrial Data Intelligence Foundation and the IoTDB 2.0 with AI ability. It mainly includes a dataset node called the data node, where we manage all data, such as time series, static, and multimodal data. It includes reading from external data sources. Then there's the AI part, managing our time series large models. It also covers processing the data and fine-tuning the models. On top of these two components is our system management part, known as config node. In system, it acts as a behind-the-scenes worker, helping manage collaborative operations and status of these two nodes. Building on this, we support a wider range of industrial intelligence applications, including construction of intelligent agents. This also covers intelligent operations and maintenance, real-time prediction and detection. Our product components, 3 parts. First, a professional time series database, a complete product. 2 extension modules, a federated query module, an intelligent analytics module. These can be plugged in as needed. Next, let's take a look at IoTDB's increasingly open and end-to-end ecosystem. So after we had this robust data infrastructure and advanced AI infrastructure firmly in place, we then brought in strategic partners for deeper integration to truly see what significant value our data plus AI can bring to various enterprises. We worked closely with a very tight-knit partner to understand their business scenario. Basically, we collected data on the daily charging and discharging of virtual power plant batteries to help regulate peak and off-peak loads. So what kind of business problems do they face every day? For example, today I might have a query where I want to analyze which batteries are involved. There are some statistical metrics, and there's also analysis to identify which batteries have charging or discharging faults, and then categorize and rank these faults. There are also some more advanced analyses, such as predicting future trends. All of these analytical needs might arise suddenly in a specific scenario on a particular day. They don't necessarily become a standard feature of the platform. So what people usually do is solve the problem first, meaning they manually extract the data and process it in various ways. All of this work is one-off. If you want to turn this into a standard product application, then you need more product design and the definition of certain processes. That could take several weeks. Even now, without standardized development, even if it's done manually, each analysis task still takes about 2 or 3 days to complete. It's actually a very labor-intensive manual data analysis job. So, is it possible to free people from this kind of tedious analytical work? Actually, it is possible. We co-developed an intelligent application that can automatically carry out business analysis. We call it business analysis because the data involved isn't just time series data. There are also static data and knowledge bases. We've enabled interaction with the database through natural language. Now, in the era of large models, natural language to SQL has become increasingly viable. This means IoTDB's SQL dialects can now be understood and used by large models. And it also makes use of our previous analytical features, such as trend queries, nested queries, and so on, allowing large models to better understand the time series data in IoTDB. At the same time, it leverages multimodal data management capabilities to associate time series data with multiple data sources, as well as aggregate business knowledge. For example, the image on the right shows the process of storing and visualizing some business knowledge within the database. Now that we have the knowledge, let's take a look at its effect. Below, you can see the business questions we've raised. These business questions might be specific to a certain application scenario on a particular day. We raise these questions with a specific purpose, such as wanting to analyze what features this data has. Then, the model will generate an SQL query targeting this raw data based on the question, and then further visualize this data to see whether the data you want to analyze is actually what you expected. In the next step, by combining the data we've retrieved with the knowledge base, we can further process and understand this data and finally produce an analytical report on it. This really simplifies the manual operations we used to do before. The model provides a rapid reference, and even if it's not always precise, it still offers significant support for human decision-making. All right, so besides the application I just mentioned, we also have a full lifecycle ecosystem. This includes data collection. And as we can see, also the data integration, computing engine, visualization, and analysis tools. With this ecosystem in place, users can easily find suitable tools for any functionality needed in their systems. IoTDB isn't fighting alone. It can be integrated seamlessly with modern AI software and tools. This often leads to surprising synergies, some of which even we might not have imagined. People can use these software combinations to create all kinds of amazing stories. All right, so taking it a step further, we've teamed up with Kaihong and deeply integrated with their edge intelligence hardware boards. This board is suitable for data management and analysis in intelligent edge IoT scenarios. It's lightweight, capable of handling millions of data points per second for writing on the edge, and supports millisecond-level queries, while also enabling higher data compression ratios. We partnered with AST and the University of Science and Technology Beijing to integrate controller. This controller suits real-time control scenarios like steel hot rolling production lines. Its features include a domestically produced CPU and microsecond-level real-time control. For example, in steel hot rolling, precision requirements are extremely high. With such high precision demands, our data collection requirements have become more comprehensive and efficient. So, for data collection, it basically needs to gather data every microsecond. With this capability, users can now store their raw data directly on the board at the edge and upload it as well. This overcomes the previous bottleneck where they could only perform control at the edge, and all operational data was lost. All right, going a step further, we developed an intelligent, all-in-one machine with IoTDB. This device is built with domestically produced hardware, pre-installed with IoTDB and other large models, right out of the box. It supports over 100 million data points at the second level, with write and query throughput both exceeding hundreds of millions per second, millisecond-level latency, compression ratios over dozens of times, and data retention of more than 10 years. So in this way, the database is no longer just software. It's a tangible product you can actually touch. Once you get your hands on this device, you can start using it right away. This is the hardware ecosystem. Next, let's look to the future. Over the past decade, IoTDB has developed and accumulated a user base, and everyone has expectations for us. In the future, we will continue to build on these expectations and enrich our offerings. A few main points. First, ease of use, freeing everyone from tedious manual operations. Second, multimodal fusion, managing data that is more comprehensive and diverse. Third, beyond just managing data, the database must manage it securely, becoming a safe deposit box for data. Once your valuable data is stored in IoTDB, it should be fully secured, unbreachable, and leak-proof. At the same time, crucial thing is that when we enable all these functions, we must maintain utmost stability. As a fundamental core tool or basic component of a platform, the database's role is not to remind users of its presence when they are actually using the application. Instead, it should be hidden within our platform, allowing everyone to simply use the capabilities it provides without needing to pay attention to the fact that there is a database underneath. This requires the database to achieve ultimate stability. Therefore, achieving ultimate stability is always our #1 goal in the database industry. Since 2016, when I first started working on IoTDB during my graduate studies at Tsinghua University, we've received all kinds of valuable feedback from users. Back in 2017 and 2018, users kindly gave us some initial evaluations, and these thoughtful comments have served as our motivation ever since. In the future, we will certainly continue to move forward step by step, further meeting everyone's expectations for IoTDB. It's also truly gratifying to see this positive progress. Now, IoTDB has become a pillar of digital transformation in various industrial sectors. Thank you all. That concludes my presentation today.